Good late afternoon, everybody. Thanks a lot, Professor Sokol, Vice Rector of Technical University, for this nice introduction. And the title of my lecture is Material Parameters and Damage Identification based on Artificial Neural Networks. And this training is based on small sample training. So in my lecture, the outline will be that I will focus on material parameters identification, mainly fracture mechanical parameters like fracture energy, tensile strength, compressive strength, based on artificial neural network of backpropagation type and training by small sample stratified Monte Carlo type sampling. Because the topic is very related to uncertainty simulation. So I will speak about Latin hypercube sampling simulation, which is special technique of stratified sampling, and how we introduce statistical correlation in our simulation model. Well, it's necessary to mention a little bit about software which is under our development, especially software freed for reliability and statistical analysis. Software SARA, which we developed in cooperation with software company Červenka Consulting, which is called SARA, acronym of Structure Analysis and Reliability Assessment, and the software to handle artificial neural networks. Of course, the most interesting will be applications which I present. The applications will be for material parameters identification at both deterministic and stochastic level. Very special application of this stuff is inverse reliability problems, which is the most difficult problem in reliability engineering. And damage identification is certainly some interest of you or Professor Sokol and his co-workers, which is also very hot topic. So this will be the main outline. Slide, parameters of numerical models. Actually, if we develop some numerical model, so we want usually that our numerical model to match the measurement performed in laboratory or in situ. How do we find parameters of numerical models? This is sometimes very difficult, and one option is to do it by inverse analysis. Typical parameters of materials, especially in case of concrete, is elastic modulus, fracture energy, density strength, etc. And we have some information about parameters. If we have experimental data, this is very good actually, but usually there is a shortage of experimental data, and we calibrate the compression model. Then we have some recommended formulas, for example, from code, ViP College, etc. And last is engineering estimation. This is actually the weak information, but very often we use that. We developed compression model, and we hope to reach, for example, laboratory experiment, and it's not like that. So we play with these three levels of information to achieve our goal, right? Actually, for example, like in this picture, let's suppose that this is some experimental result of load deflection. Okay, for example, 3-point bending, right? And from experiment we get the red curve. Our model, even we get parameters from relatively good experiment. So our model is, for example, this black one, and it doesn't correspond. Okay, purposely I amplified this big difference, right? Of course, why? Because parameters are wrong, experiment is contaminated, our model is contaminated. There is a lot of bad influence which influence this difference. What we are doing usually, so correction of parameters, and by just simple trial and error method, right? This is a typical what we are doing, but there are actually sophisticated identification techniques which can be applied to update parameters to improve our model to be closer to experiment. One approach can be inverse approach to stochastic analysis, which is combination of artificial neural network and stochastic calculation. Well, a few words about artificial neural network. Maybe somebody of you already knew it. So engineers or mathematicians took it from just to model the processes in nature. So artificial neural network are supposed to model processes in brain. It's based on McCulloch-Pitts perceptron, which was presented in 1943. And nowadays, artificial neural networks are actually very widely used in engineering, in technical practice, not only in engineering. Neural network, you can see this is something what we have in our brain. And there is an input layer, there is an output layer, set of neurons are arranged in several layers. And these neurons are connected with each other to all neurons in following layers actually by weights and biases. Okay? And this is a mathematical model, this is a reality, and in reality, we train the network, we calibrate, we determine weights and biases somehow, and this is a mathematical model, right? This is the structure of neuron, where Y is neuron output, K is the number of input impulses, P is input impulses in one neuron, and there is a weight coefficient and bias neuron which are unknown and should be trained. Function F is very important. Actually, this is a transfer function which model the transfer between neurons. There are several parameters of the neuron. Actually, the behavior of the neuron is determined by first synaptic weights. This determines conductivity of connecting paths, then biases, and transfer function. Sometimes it's called activation function. And usually several types of transfer functions are used. Linear, nonlinear, etc. In this picture, you can see hard limit transfer function, which is just hard limit, linear transfer function, and finally in picture C, there is a nonlinear transfer function, for example, some sigmoid. Of course, you can estimate that if we model nonlinear behavior in engineering mechanics, for example, so what type of transfer function is the best? Of course, also nonlinear transfer function, because nonlinearity is always captured better by nonlinear function. So, actually, neural network, working with neural network, there is input variables and output variables on one side of networks, and this is the food for training of neural network. And this food is actually, it comes from measurement, or it can come from virtually produced measurement. I mean, by virtual realization. Working with artificial neural networks is working in two phases. First of all, the network should be trained. This period is called adaptive period, right? In this case, network should be trained in order to determine weights and biases by realization by sets of P and Y. After that, second phases, which is of course reward why we do this training, it's simulation of the process. It's an active period. Once the network is trained, then if you provide any vector P, neural network will tell you what is Y. If you provide Y, neural network will tell you what is P. So the beauty of neural network is actually that it's approximation of some process, and it works from P to Y and from Y to P, from input variable to output and vice versa. So normal, for example, multi-regression analysis is going just in one direction. And this is the reason why we efficiently use this artificial neural network for inverse analysis. This, because it goes in both directions. Okay, so training of network is determination of weights, biases, and transfer function. And in order to train the network, we need n pairs of input and output vectors pi and yi. And as I mentioned, this is actually many engineering application is based on approximation of some processes between input and output where the model is actually not known, right? In our case, we run model with various sets of parameters y, and input vector p is model response, for example, structure response, low deflection curve. And then optimal weights, bias, and transfer function are those minimizing norm during the training of the network. So it's actually some sort of optimization process to train the network. Actually, the norm is minimized, and different type of optimization techniques can be used, like gradient descent method or gradient descent with momentum method. Levenberg-Marquardt is typically a very famous method. Newton, also simulated annealing, etc. All these networks are called so-called backpropagation types. And this is something which I hope will give you the idea how we identify parameters from single low deflection curve. For example, records of experiments are often low deflection curves, just 3-point bending, for example, notch or notch specimen or anything like this, has force versus deflection, and this is the result of experiment, right? We put the points on low deflection curve, for example, maximum force or deflection, or let's say pairs of force and deflection on low deflection curve, as input parameters of the network. To this low deflection curve, some outputs corresponds, and these outputs are actually parameters which produce this low deflection curve, which are corresponding to this low deflection curve, like material model parameters, okay, fracture mechanical parameters, tensile strength, compressive strength, etc. And if we are able to have the model where we generate these outputs, and by finite element technique or nonlinear fracture mechanics type, we produce several low deflection curve. So we have set of outputs and set of inputs, and in such a way we will virtually create the training set for the network, right? And then we can answer the question if we have experimental curve. So we just put the points on experimental curve, and after network is trained, then it will answer the question, what are the best parameters for specific curve? Okay, and this is this beauty, as I emphasized, that we go, let's say, from low deflection curve to input parameters and vice versa. In reliability engineering, we need to identify statistical parameters. Actually, we have two approaches in this case. We can have low deflection identification approach one by one, that material parameters are identified individually for each specimen. And then we get the set, and we subsequently we make assessment of parameters of all specimens. There is another approach which we developed with my colleague, direct statistical parameters identification. Because a random response of a structure is available in form of histogram and statistical model. And then we go directly to identification from statistical point of view, and the statistical parameters are direct output of inverse analysis. I will speak it about later. Again, this is the scheme of this direct approach. Once again, so we developed computational model where we have material model parameters here, for example, parameters of concrete or steel or anything, what you want, right? We simulate them by Monte Carlo type approach. The best is hypercube sampling because it reduces number of samples to minimum. To each realization, finite element method computational model will produce structure response, okay? And then we have a set of material model parameters, we have a set of structure response, so of even bundle, and this is the food for training of the networks. After the network is trained, we supply experimental curve here on this side of the artificial neural network, and the best parameters are selected. So this is automatic type of the analysis. Now it's necessary to say about uncertainty simulation, because this uncertainty simulation is used for small sample training of the network. We use so-called Latin hypercube sampling, the technique which was invented by Huntington and Riddinsis, based on simulation of the mean value. Each random variable, which is randomized parameter for training of the network, is represented by distribution function and corresponding probability distribution function. And distribution function is divided into n-sim non-overlapping intervals. And from each interval, we select realizations. Actually, one interval is used only, each interval is used only once, and this is the beauty of hypercube sampling, that the space of random variables, even in multi-dimensions, it's covered quite regularly, right? This technique, where the mean value from each interval is selected, is based on this formula. This is actually, it reminds you mean value from statistic, but this is an interval A and B, some specific interval A and B. If here is minus infinity, plus infinity, this is definition of the mean value actually, right? But we sample from each interval, so this is the YE related to each interval, where these are the boundary of the interval. So you can feel that if you produce realizations using the mean value of the interval, so from the definition, mean value will be produced very, very well, almost precisely, right? This is the beauty, that sample averages equal exactly the mean values of variables, and it has been proven that variances, even higher statistical moments are much closer to target values compared to other selection scheme. For some probability density functions, including Gaussian, exponential, Laplace, etc., the integral can be solved analytically. There is an integral from A to B, but in some cases it cannot be solved analytically, and we have to do numerical integration. But this effort is actually, it will pay off. It's worthwhile. Well, concerning statistical correlation, you know that in stochastic engineering mechanics, we have to produce statistical correlation. We have to impose, for example, that between fracture energy, tensile strength, and compressive strength, there is statistical correlation, which is expressed by some correlation matrix, right? How do we solve this problem? If you see this simulation plan, where in columns you have random variables, and in rows you have individual simulation, simulation 1, 2, until simulation and sim. So this is just simulation plan of statistical sampling. We need to prescribe correlation matrix T, okay, where we have, for example, correlation coefficients 0.8, 0.7, or even negative, etc. If we randomly generate, there is correlation matrix A, but we need T, not A. We construct difference matrix, so-called error matrix, as E equal T minus A, and we impose suitable norm of this difference. For example, Euclidean norm, right? And we search as an objective function minimum among all possible rank combinations. We determine this norm. Actually, we can do it by force without any special techniques. For example, see if we switch realizations, okay, then any switch of realization will influence correlation matrix. So we can do it randomly, or we can even explore the whole simulation space. But this is not very good, because from permutation mathematics, from combinatorial mathematics, there exists n simulation, number of simulation, factorial to the power of number of variables minus 1 possibilities, which is even for small number of simulations and for small number of variables, this is extremely big number to treat that. So that's why this is impossible, or very primitive approach, and we proposed approach which is called which is based on simulated annealing technique. Simulated annealing technique is the sort of optimization technique, and it belongs to category of stochastic optimization technique. The beauty is that there is a probability of escaping from local minima. So, and actually this probability is driven by Boltzmann probability distribution, right? Where its energetic analogy with annealing of the crystals. Again, we simulate the nature in some case, and step by step at the beginning we impose very high energy and very high probability of escaping from the local minima. So have a look, for example, this energy landscape, and this is a ball. If I take this energy landscape and I will shake at the beginning very randomly, very widely, so the ball is jumping from local to global minima and vice versa. Then I decrease the level of excitation, so it means I decrease the system excitation. Okay, so first like this, and after that very small. At final point, the ball will remain where? In global or in local minima, I don't know. But during this process of annealing, I will remember the lowest position, okay? And And there is a very high probability that such stochastic type of optimization will really reach global minima. And we applied this technique for imposing of statistical correlation, and we found that it's much better, this correlation control, in comparison to Cholesky decomposition and other techniques which are used in reliability engineering. User of software Fried actually appreciate robustness of this technique. This slide showed so-called hierarchical sampling. Actually, in standard Monte Carlo technique, you can add simulation as you want. There is no problem. You perform 20 or 50, and you want to make better results, so you impose next 50 simulations, and these first simulations are not lost. So you can count that. But in case of hypercube sampling simulation, the situation is more complicated actually, because in hypercube sampling scheme, it is necessary to specify the number of simulations in advance. And we overcame this by hierarchical Latin hypercube sampling, where we solved the problem, the addition of simulation to the current sample set. Because in stratified sampling, hierarchical refinement of sampling probabilities is needed while maintaining the desired correlation structure using this correlation control. It's actually shown in this picture that in hypercube sampling we have to refine the probabilities in some specific scheme, that from 2 we have to go to 6 to 18, etc. We can call it as a cascade samplings, and this can be fully automated, and this hierarchical sampling will allow us to add additional sampling, and this is also important for increasing the accuracy of training of artificial neural networks step by step. Okay. Well, sensitivity analysis, what we are using is non-parametric rank order correlation coefficient between input variables and output response variable. We use statistics Kendall tau or Spearman coefficient of correlation, and it works in such a way that if we have in simulation variables and a result, so then instead of real values, instead of absolute values, we switch to orders, to rank. So these reds are ranks, and these ranks are used to calculate correlation coefficients. Actually, it's additional result of hypercube sampling simulation. No additional effort is needed, and bigger correlation coefficients mean higher sensitivity. And the relative measure of sensitivity in our model is between -1 and 1. And if we get sensitivity correlation coefficients, non-parametric rank order, which is, let's say, close to 1, so conclusion is that this variable influences the output very much. If it's close to 0, there is no influence. It sounds maybe that not always is needed, but in computational model where we have 200, 300 random variables, we really want to distinguish between dominating and non-dominating variables. And sensitivity analysis is for that. Finally, reliability analysis. Because we are constrained by extremely small number of simulations, like tens or hundreds, very often we calculate reliability, failure probability by Cornell safety index or by K-fitting or by first order reliability techniques, which are the sort of techniques which uses relatively small numbers of repetitive calculation of the model. And I will show you some example. First example is Meyer shear wall test. This is quite nice test of shear wall. There was a horizontal force, a vertical force, and actually the foil by the wall failed in experimental laboratory long time ago in Germany by diagonal shear and by crushing of the concrete in this part. And actually, in this case, this is an experimental curve here. And Vladimir Červenka actually had at that time really trouble to calibrate the parameters for that. We did, that's why we took this example as a testing example, where there was a training set of 20 random realization of random low deflection curve. You can see it here, okay? And you can see that actually none of this curve copy exactly experimental curve, right? But this bundle of low deflection curve plus set of realization was the food for neural network. And we wanted to capture the best this experimental curve. At some level of deflection, here, and here, we did also sensitivity analysis, right? This is actually a computational model in Athena software, where you can see this is the experiment, crushing concrete here, and this is the model and low deflection curve just at some specific step. And after the training, actually, we had two versions. Sensitivity analysis resulted in, we consider 6 or 10 random parameters which were there, and after identification of these parameters, we get very good agreement with experimental curve, which was hardly done by, let's say, trial and error approach, because it was the complicated combination of parameters, especially in this region. So this is the result of calculation after identification. I hope I have it here. Oh, sorry, this slide should be maybe before. Actually, here is a result of sensitivity analysis, non-parametric Gordon correlation, highlighted some levels of sensitivity analysis, and these are selected 6 and 10 parameters for identification. I will switch to damage identification. At some point of working with artificial neural networks, we realized that the whole methodology can be used actually for damage identification. Why? Because this is very often the part of health monitoring of the bridges, and in dynamic testing we are working with eigenvalues and eigenfrequencies. So these are the dynamic measures which can be used. Any damage will change these properties, this characteristic as eigenvalues and modes, right? And mode shapes. And this is actually the key point. So again, we virtually simulate the damage and parameters and observe the influence of eigenfrequencies or modes, and then we supply what is measured, eigenfrequencies and modes, and then hopefully we can get location and amount of the damage. We did something, an application of damage identification in one specific bridge, which is called the Izarko Bridge on Brenner Highway in cooperation with Austrian colleagues. It's a cantilever beam, actually, fully post-tension box jadder. These are parameters, and there are more than 200 pre-stressing strands. So actually, the model, even in 2D Athena, was quite complicated. It was a part of the bridge only. So, and actually, the bridge girder was discretized into 31 parts with independent bending stiffnesses EI1, EI2 until EI31, and this was the subject of identification, right? There was 5 eigenfrequencies and corresponding mode shapes were studied actually, and damage of girder was modeled by decreasing of bending stiffnesses in some girder. So EI was, let's say, virtual damage to 10 to 90% of its nominal value. And these pictures show actually just a parametric study, the relative change of eigenfrequencies, of some selective eigenfrequencies. Here is the F2, F3, in girder part index and as a parameters of relative stiffness of the girder. So, and this is actually the result that we were able to identify the damage based on let's say measurement of eigenfrequencies and mode shapes. So this is undamaged, and this part is a damage. And in this case, this was let's say virtually influenced in this bridge. This was a testing example, and result of identification was this was a damage, and detection of the damage by neural networks was captured in such a case. There is some pathological behavior close to the support, but more or less the damage has been captured. Damage identification is complicated task because there are many techniques which can detect the damage, but the weak points of this damage identification, according to my feeling, because I'm not dynamic guy, but I touched it only a little bit, is that honestly speaking, damage should be quite big if we really identify the location and the level of damage very well. So of course the effort is done in order to identify also very small damage, but I am very skeptical about this. I know Professor Sokol is working in this direction very much also, and other people. Actually, this is after neural network. Again, it is appeared in my slide. There are first, third, and then fifth modes, and this is actually, for example, demonstration of third mode shape, that there is an undamaged distance along the girder, right? Damage state, and then identification by neural network, which fits relatively well. So the damage influence these mode shapes, and it's a question how many frequencies, how many mode shapes is necessary to consider. Again, this scattered table is supposed to contain information on random variables related to this bridge, going from modulus elasticity, tensile strength, is a fracture energy, etc., related to concrete and steel. This was used for calculation of reliability. After that, you can see the finite element model behavior in bending and shear using the random realization. Here it was quite interesting that even at the level of random variables, behavior of the finite elements of failure mode it changed from bending to shear. So approximately 60% of the samples failed in bending, 40% in shear. So it means the designer of this bridge did really good job, that it's quite balanced, right? The mode of failure. And after application of this type, we were able to calculate reliability index profile versus degradation, reduction of pre-stressing strength in time. So without also degradation of carbonation, using carbonation depth and corrosion of this pre-stressing strength were implemented in order to be able to model decrease of reliability in time. Okay, and this is for different coefficient of variation. It's just one of output of that. So the aim of to identify damage and then to calculate reliability. Because 3-point bending of fracture mechanic of fracture test, notch specimen, this is a standard test for fracture testing. And the group at my institute is of Zbigniew actually is focused very much on this testing, right? And we do it routinely, very often. Inverse analysis tool, so-called frame pit 3-point bending tool, has been developed, and this allows us identification of parameters of experimental data, of 3-point bending experimental data. It's designed for concrete of various strengths and ages, and we produce a very large training set for artificial networks, and we train it just once. And the result of training were implemented directly in this tool. So the aim was actually to develop the tool where if you go to laboratory, you produce low deflection curve, you put low deflection curve in the software, and in the software artificial neural networks is directly implemented, and software will tell you immediately what is fracture energy, what is tensile strength, what is compressive strength, etc. So actually this is very useful, especially in case of laboratory where this testing is done very often, right? And this was our case because we highlight this testing as an experimental computational determination of fracture mechanical parameters which are used consequently for fracture mechanics finite element modeling of the structures, right? And at the moment we even transferred some specimens from colleagues in Vienna. This is actually robust neural network is implemented and trained. There is a significant time reduction compared to general identification task. There's no need to handle it because it's just one strains. And subject of identification are these red parameters, which are the key point. And there is a connection to Athena software, and this is a structure of network and identification, right? Actually, last year we did quite large experimental testing campaign of stochastic properties of various concrete types, mixtures and ages, even fiber reinforced concrete, in cooperation with one company and university in Vienna. The aim was actually to do a comparison of fracture mechanical parameters obtained from several testing configurations. Our laboratory concentrated to 3-point bending test of notch specimen, but in Vienna also wedge splitting were done. And we are now developing stochastic property database. So this is just another part of the puzzle. In order to know statistical moments, distribution functions, and correlation coefficients. In this case, about 160 beams have been tested, so it's in our environment, it's quite big test, right? I just show only some specific tests which were tested. Set 1, this concrete, 9 specimens, age 91, etc. Usually this number of specimens allows us already some setting of statistic, which is the beauty. And we, for evaluation, we use this material parameters identification based on artificial neural networks. So these are, for example, results from experimental campaign, right, and identification. So just selected set of parameters of concrete. Neural network identification resulted in these values and coefficient of variation. Beauty is that tensile strength can be captured, because tensile test is always difficult, almost impossible to do under normal condition. And some parameters evaluated by working of fracture technique, which almost correspond quite well. Identification and direct experiment are in very good agreement, actually, in this case. So this is another set of concrete, so I think this is boring, so I can switch it. I just only wanted to show you the, let's say, the enormous testing. These are comparison of these three fundamental fracture mechanical parameters, which rules failure and crack propagation of the concrete, right? So this is after experiment identification. After a calculation, you can see we are very close in low deflection curve in both pre-peak and post-peak region. Conclusion of this experimental campaign is actually effective crack is actually this synthesis of these parameters. These are recommended statistical parameters for stochastic nonlinear finite analysis made of tested concrete. So, and these are actually for some girder beams where one part of division of the Krug company actually use it for design. So these are shear beams which are now under development. Another application is some jointless bridge casting here. There was testing campaign has been done and material parameters identification were done. This is numerical model or crack patterns in Athena software. Just the part of the bridge has been evaluated here. Okay, and these are random low deflection curve for reliability analysis. And again, fracture mechanical parameters were identified based on specimens of the concrete of this bridge, right? So we were quite good information for concrete parameters from identification. Also correlation matrix has been estimated. And this was the stochastic model where we went to reliability analysis, and the result of reliability analysis for ultimate limit state and serviceability limit states are in these pictures, compared for ultimate limit state with Eurocode 4.7, and this is just the decrease of reliability index related to mean value of the loading. In serviceability limit states, the picture is, let's say, more colorful because there are different deflection limit of the span under different specification. Is different from in Eurocode or US standard specification, so we have more here. Another application of the whole process was actually press-treated railway sleepers, where SARA calculation has been used for estimation of probability of maximum crack width. The railway sleepers are tested in shear. This is a typical test, and they were interested actually in some nomogram of probability of occurrence of the cracks versus maximum crack width for different level of shear load. This type of nomogram we provided them for some decision making and the design, right? And finally, conclusion. I tried to show you that I and my team, from longer perspective, we are trying to develop and employ stochastic simulation techniques and advanced tools for probabilistic assessment under the name of Freed software. Degradations are until Freed-D software. SARA is a combination with Athena, finite element computational mechanics software, right? And this we used. And material parameters and damage identification based on artificial neural networks is a part of soft computing story which came into existence as a more or less as a first side product, and second as something what we needed to identify parameters especially. Okay. Thank you very much for your attention, and I'm waiting for your critical question.
Thank you for a nice, interesting presentation. There were many topics included, so I think you have questions. So maybe I'd like to ask something. So in case of damage identification breaches, it's necessary to perform the training of neural network using a statistical method, or it's also possible to use only few experimental data. For example, you can use measurements of eigenmodes and eigenfrequencies repeated many times, and this can be a search for the neural network trainings, or it is necessary every time use statistical simulation via Monte Carlo method or similar?
Yeah. It was not very visible. Thanks for this question. So it's very. I will try to figure out. Actually, measurement in this damage identification is supposed to be done like we have eigenfrequencies 1, 2, 3, etc. Mode shapes 1, 2, 3, etc. And we measure. Okay, dynamic people measure this. And let's suppose it is a crisp value. It's just fixed one value. Yeah. Then, if we want to identify damage, so we develop a finite element model. This example was done actually in sophistic software, which produce eigenfrequencies and eigenmodes, no problem. And then we consider stiffnesses, and we simulate. If we take, let's say, nominal value of stiffness, so there is undamaged structure. And now these stiffnesses, we change randomly to influence so-called damage in these stiffnesses. If I change the stiffness somewhere in the beam, it's supposed to influence eigenfrequency, eigenmodes, right? So it's happening, really, in the model. On one side of the network, I have realization of random stiffnesses. On second side of the network, I have eigenfrequencies, eigenvalues, right? I train the network. Then I forget about finite elements. I have network. And I pick up what dynamic people measure on the bridge, real experimental data of eigenfrequencies and eigenmodes, right? I put to network, and neural network will tell me, well, here is stiffness like this, another stiffness, And this was what this location and level of damage is hopefully assessed based on this procedure. So concerning experimental data, I don't have statistics so much. So I just keep to deterministic. So statistical simulation is used just to approximate the finite elements to have a model where I put eigenfrequencies and eigenmodes, and the model will tell me location and the level of damage, which none of finite elements can do that. Yeah, so finite elements can simulate, of course, response of any type, low deflection or eigenfrequencies, where you put geometry, material, load. That's it, not vice versa. So, yeah. Mm-hmm.
Thank you very much. Is there any other question?
You have shown us the relation between force and displacement for displacement of 3-point test.
Yeah.
This equipment, do you have in your department?
Yes, we have this so-called vlaštovka in Czech. Yeah, there is some special tools for this which we developed. Yeah.
It must be equipment which is a servo-dynamic system.
Yes.
Rather expensive.
Yeah. I know because actually this low deflection curve is there are several problems actually, and the main trouble is that the experiment should be set up very carefully and precisely. There should be this steel tool over the beam, and the whole process of loading, the rate of loading should be very small. So really we just break one specimen. Maybe in some cases it takes 15-20 minutes. I mean, really very slower better, right? I cannot tell you number exactly here, but my colleague really takes care because if you do it this testing quite in not very good machine, not very well set up and quite quickly, so then there is a catastrophic behavior. After the peak, it goes very suddenly, and my colleagues also developed some special approximation technique which approximates this point in pre-peak, in post-peak behavior, right? Because this catastrophic behavior, let's say, destroy almost everything. So we have to take care about this post-peak branch very much. Even in some cases of fiber reinforced concrete where the post-peak branch is very long, so this catastrophic behavior is also quite complicated. I have one example. We worked with some Austrian colleagues, and they ordered in some professional testing company, high price for testing, so they did it very, let's say, as a routine fracture mechanics testing, but these low deflection curves were terribly, just garbage, okay? So we hope that we are doing it better, and I promoted via Institute of Structure Mechanics, but this is the part of, let's say, experiments which is under our umbrella, and it's so related, it's so much related to let's say, computation, that we highlighted that we are doing it in professional way. I hope so.
At the end of this lecture, it's my honor to hand over, in the name of our rector, certificate of honorary membership of the Visiting Professors College STU. Thank you, Professor Novák.
Thank you very much.
Very nice presentation.
My pleasure.